Right. So one of you tell me, let's say there is a flat ground, okay? Large open ground, it's flat, it's not tilted. And a vehicle is taking a turn on it. We had talked about this in the last class. The force responsible for helping us take a turn is friction. Okay, without friction from the ground, it's not possible to turn. And you all must have experienced this in real life also. If the road or the path gets slippery, it becomes difficult to take the turn. Okay. So think carefully and answer this. Suppose a vehicle is smoothly taking a turn. Okay. Or I should say gently taking a turn. Gently means without slipping or skidding. Okay. You all know that friction is needed to take the turn. So if the vehicle is gently taking a turn without skidding, what type of friction must be helping the vehicle take the turn? One of you quickly tell me, what are the two types of friction we talked about till now?
Static and kinetic, sir.
Static, kinetic, correct. So when a vehicle is moving forward and taking a turn without skidding, what type of friction helps the vehicle take the turn? I
Static
want answer.
frictions.
I want answer from all of you. Okay, Vanilla is saying static. Others, what do you think? I got one more answer as static. Rishi, what do you say?
Sir, but isn't static like it like it's like between a stationary object, right?
Okay, you consider whatever factors you want. Give me your answer. Is it static or kinetic?
Sir, I think it's kinetics.
Okay, I got two more for static, one for kinetic. Aishwarya, you are the only one left. What type of friction do you think is acting?
So static friction.
Static friction. Okay, fine. Good. Rishi, the answer is static friction. It is clearly mentioned here that the vehicle is taking a turn gently without skidding. Okay, we had discussed this when we talked about friction. Like suppose a person is walking. Fine. If you are walking, like to walk, we need friction. We need the help of friction. And if you are walking without dragging your feet or without slipping, the kind of friction helping you is static friction. Okay. See, static friction or friction in general doesn't have to keep the object at rest. Object can move. The object, wherever it touches another surface, is it skidding there or is it not skidding? That is what matters. Okay. So when you are walking on the floor without skidding, friction is helping you walk and there is no skidding. So the kind of friction helping you is static friction, not kinetic friction. Same with a vehicle also. See, for a vehicle to accelerate, friction is needed. For a vehicle to slow down, friction is needed. For a vehicle to take a turn also, friction is needed. If no skidding is happening, the kind of friction helping in all these processes is static friction. Okay. Object doesn't have to be stationary. The two surfaces that are in contact. In case of a vehicle, the tire and the road, okay, must not slide over each other. The tire should not skid. It can roll without skidding. Okay. We'll discuss more about rolling without skidding in the chapter system of particles. Okay. 2 chapters after this. But remember, if there's no skidding happening, the kind of friction helping is static friction. Okay. Static is correct. Fine. Can one of you tell me what is the limiting value of static friction? Or what is the formula for limiting friction? That's my question.
Mu n, sir.
Mu into n, correct. Mu s, coefficient of static friction, multiplied with the normal force between the vehicle and the road. Okay. Now we are talking about a case where a vehicle is taking a turn on a horizontal surface. Fine, just a moment. Right. So situation is actually like this. So suppose there's a curved road, basically a turn. Okay. The left part of the image is not necessary actually. Anyway, or just a moment. Okay, let's take it from here itself. Okay, consider this. So basically there's a curved road. Fine. The car is taking a turn like this. Now this road, the way it is curved, it has a particular radius of curvature. Every curve has a radius of curvature. Okay. Now you can imagine this road to be part of a circle. Then that circle's center would be somewhere here. So the distance from here to here is what you call as the radius of curvature of the path in which the car is moving. Okay. Let's say the car at this particular instant is moving with a speed v. So basically it's an object moving with a speed v, taking a turn of radius r or along a curve of radius r. Now you all tell me, if an object moves with a speed v along a curve of radius r, how much radial acceleration should it have? What is the formula for radial acceleration or centripetal acceleration?
V square by R.
V square by r. Correct. Fine. Now in this diagram, they have shown the forces acting on the car also. Its weight will be acting perpendicular downward, that is into the road. Okay. Mg will be acting into the road. There's a normal force acting upward, okay, from the road. But see, the normal force and the weight of the car, they are both in the vertical direction, but the turn has to be taken horizontally. Okay, on the ground it has to turn, right? So it's a horizontal turn. Parallel to the ground, it has to take the turn. Normal force and mg are vertical forces. They cannot help this car in taking a turn because they won't have any component in this direction. Okay, to take a turn, we need some force acting towards the center of the curve. Fine. So basically what happens, had there been no friction, the car would have gone straight. It would not have taken the turn at all. So it would have slipped outwards. Okay, it would have skid radially outward. Skidding would have happened in this direction. It has a tendency to skid this way, away from the center. Now, if the tendency to skid is that way, then naturally friction, okay, on the tires is going to act in this direction. That is what they have shown in the diagram. Fs, static friction, is acting radially inward, and that static friction is what helps in taking a turn. Fine. There is an assumption we are making here. Unknowingly, we are making that assumption. We are assuming that the speed of the car remains constant while taking the turn. Okay. Suppose speed has to increase. Now speed increase and decrease is done by tangential forces, not radial forces. Radial force changes the direction. Tangential force can help the object speed up or slow down. Now, suppose this person, the driver, when taking the turn, is pressing on the brakes. So slowing down and also taking a turn. Now for taking a turn, we need this radial force, friction. For slowing down also friction only is needed, no? So in that case, if brakes are applied, friction has to act this way also in the tangential direction. as well as the radial direction. Okay. Suppose while taking a turn, the car is speeding up. Okay. Some people do that also. It's dangerous, but sometimes they speed up while taking a turn. To speed up also you need friction. Then in that case, what happens? Some friction acts this way in the forward direction and some friction acts radially inward. So see, it's not like two separate frictions. Effectively, friction will be acting in this direction. One component this way and one component this way. Okay, two components of friction will be there. But for now, let us discuss the case where the car is taking a turn without any change in its speed. If speed is not changing, speed is constant, tangential force is not needed. But direction has to change. It's moving on a curved road. The car is taking a turn. So radial force is compulsory. So there must be static friction acting towards the center of curvature. This point here is called the center of curvature. Okay. So static friction provides the required centripetal force. I was telling you in the last class also, centripetal force is not an additional force that acts on the system. Whatever net force acts towards the center, that itself is called centripetal force. The three forces acting on the car here are normal force, its weight, and static friction. Static friction is the one which acts towards the center. Therefore, while turning on a horizontal road, okay, static friction is the centripetal force. Do any of you remember the formula for centripetal force that we discussed in the last class? It comes from this centripetal acceleration. Formula for centripetal force.
mv square by r.
Correct. Acceleration is v square by r. Then force is mass into acceleration. Therefore, required amount of friction is mv square by r. That much friction is needed for the vehicle to successfully take the turn without skidding. And what friction is this? Static friction. So this should be less than or equal to the maximum friction that is available. You can't expect friction to be more than the maximum value. Okay. So whatever friction is needed to take the turn should be less than or equal to the maximum available friction. And maximum available friction is mu s multiplied with the normal force. Therefore, to turn without skidding, mv square by r, that's the necessary amount of friction, should be less than or equal to mu s into the normal force here will be equal to mg. Why will it be equal to mg? Because the vehicle is turning on a horizontal road. Its height above the ground is not increasing or decreasing. It is staying at the same level and taking a turn. Means vertically the forces should be balanced. So normal force should be balancing mg. So you can write mu s into normal force is mg. Mass gets cancelled. Send radius to the other side. You get v square less than or equal to mu s r g, or v less than or equal to under root coefficient of static friction into radius of the turn multiplied with g. So what we got here is the maximum safe speed with which the vehicle can take a turn. Now you all must have experienced this in daily life also. If you go too fast into a turn, you may not be able to take the turn without skidding. Okay, there is a maximum speed with which you can take a turn safely. If you go faster than that, the vehicle will skid. You won't be able to take that sharp turn. Okay. So the maximum safe speed with which you can take a turn without skidding is this mu s into r into g. Definitely, as the formula suggests, greater the coefficient of static friction between the tires and the road, greater the speed you can maintain. Okay, that's why you should use tires which are, I mean, of course, you can't change tires whenever you want, but depending on the need, the proper tire has to be used. Suppose you are expected to ride more on the road, then you should use tires which are designed for use on the road. Suppose you are expected to use the vehicle more off-road, then you should use off-road tires. They provide better grip in mud and all. Okay, so coefficient of static friction varies between the depending on the nature of surface, right? So if it's a normal blacktop road that you are expected to turn, one kind of rubber will be suitable. It provides the best coefficient of friction. If it's a cement road that you are more expected to use the vehicle on, then another kind of rubber will be suitable for that. It will provide a better coefficient of static friction. So that way, depending on the nature of the tire, there is a maximum speed that you can maintain. And the next thing you see here is the radius of curvature. Obviously, if the radius of curvature is more, that means it's not a sharp turn. Okay, small radius of curvature is a sharp turn. Large radius of curvature is a gentle turn. Gentle turns can be executed with greater speed safely. But if it's a sharp turn, you'll have to slow down. There are more chances of skidding if the turn is sharp. So the formula also suggests the same thing. If the radius of curvature is less, the maximum safe speed will also be less. Okay. And of course, it depends on gravity, acceleration due to gravity, because gravity is what presses the tire onto the road. Okay, so it helps in generating more friction. Right. So when a vehicle is taking a turn on a horizontal road, remember, if no skidding is happening, it is static friction that helps us take the turn. And static friction itself provides the centripetal force. Okay, let's solve some problems based on this. First, okay. Let's say a vehicle is moving with a speed of 10, okay, I'll give you in kilometers per hour. Let's take 54 kilometers per hour. It is moving at that speed, okay? And it has to execute a turn whose radius of curvature is, let's say, 20 meters. Okay, it has to take that turn whose radius of curvature is 20 meters. You know, acceleration due to gravity is 10 meter per second square. Calculate the minimum value of coefficient of static friction between the tires and the road such that the vehicle can turn without skidding. Solve this quickly. I got one answer as 7.5. One answer has 14, another has 9 by 8. 9 by 8 is 1 point something. We'll see. It's a direct application of this formula, that's all. Okay, or see, I suggest you always think from the basics, not in terms of the formula. Now, you know it is static friction which helps us take the turn safely without skidding. Okay? And static friction has a limit, mu s into n. When the vehicle is moving on a horizontal road, normal force is equal to mg. So this is the maximum available friction. This value, the maximum friction that is available, should be less than or equal to the required friction. And what is friction required here for taking a turn? So we'll we'll take it as mv square by r. Taking a turn means centripetal force. Okay. So limiting friction should be less than or equal to the centripetal force. That's the idea. Only then we can safely take the turn. Okay. That's all. You need mu s. So send g to the other side. Coefficient of static friction should be, okay, wait. Limiting friction should be less than or equal, not less than or equal to, it should be more than or equal to, no? The required force should be less than the limiting force. Required force is the centripetal force, should be less than or equal to the limiting force, right? Should be this way. So you get mu s greater than or equal to v square by rg. And v square, I don't know, some of you seem to have squared 54 as it is, should not be done. You have to ensure that all quantities are in the same system of units. Okay, so you have to ensure all of them are in SI units first. 54 kilometers per hour is how many meters per second?
15 meter per second.
15 meter per second.
15. Okay, so it's 54 into 5 by 18. 18 threes into 5 is 15 meters per second. That's the speed of the car. So 15 into 15, v square divided by the radius of curvature is 20, g is 10. 15 is 225 divided by 200. So 25 8s, 25 9s. The correct answer is 9 by 8. Okay. Others, like, think for yourself what mistake you have made. Okay. And see, 9 by 8 is a value greater than 1. Usually, coefficient of static friction will be less than 1 only. You can make it more than 1. If some sticky substance is applied, then coefficient of static friction, you can increase friction to a very high value also. If you intentionally make the surface sticky, it can be done. Okay. Here we got an answer 9 by 8. Without applying any sticky substance, this is not possible. With application, it is possible. Okay. Anyway, for taking this turn safely, the required coefficient of static friction is 9 by 8. Okay. Now try this question, all of you. Think carefully. A car moving at a speed, let's say, okay, let's assume it is moving much slower, 36 kilometers per hour. And accelerating, I should say, speeding up at a rate, say 1 meter per second square. Huh. Is taking a turn of radius, let's say 50 meters, large radius. Okay. Calculate the minimum required coefficient of friction such that the car does not skid. So this car is taking a turn while speeding up also. Okay. Everything is happening on a horizontal road. Try this, all of you. Hope you all have noted these values. The speed of the car at that moment is 36 kilometers per hour. It is speeding up, means its speed is increasing at a rate of 1 meter per second square. Turn radius is 50 meters. We need the coefficient of static friction. You can imagine the situation to be like this. So see, the point at which the car is right now moving, it's not a straight road. Okay? So you can actually consider the road to be a part of a circle like this. Fine. I've not drawn a perfect circle, but you can think of it as part of a circle. And that circle will have a certain radius, okay? That is what we call as radius of curvature of the path at that moment. The path need not actually be a circle, but whatever curve is there, we can assume it to be part of a circle. And that circle of which this curve is a part, that circle's radius is what we call as radius of curvature of the path. Okay, hope this is clear to all of you. Just a moment, let me make this circle better. Yeah, so This is kind of the situation there. Now the car is moving forward, so it has velocity in this direction. Can one of you tell me its velocity or speed in SI units? 36 kilometers per hour is how many meters per second?
10 meters per second.
36 into 5 by 18, 10 meters per second, correct. That is its speed at this moment. Now this car has to take a turn. To take a turn, centripetal force, centripetal acceleration is compulsory. Now this is the top view, obviously you all can understand that. Now to take a turn, as I said, you need a centripetal force. So there must be some force acting this way towards the center. I'll call it FC, centripetal force. And this car is also speeding up, right? To speed up, you need a tangential force. Means you need force in the same direction as velocity. So there must be some force acting this way also, in the same direction as its velocity. Ft, tangential force. Can one of you tell me what forces act on this car? Don't say centripetal force, tangential force, that is meaningless. Okay, what are the actual forces acting on this car?
Sir, mg.
Its weight will be acting. In which direction will the weight be acting?
Downwards.
Like on this screen, how would you describe that direction?
Like,
You can say it is into the screen. Okay,
yes, sir.
you are
into this.
viewing from above. Okay, right. So mg is into the screen, correct? What other forces act on the car?
Normal and friction, sir.
Normal force will be acting out of the screen. Friction is the only force which acts parallel to the surface of contact. Means in the plane of motion of the car, there is only friction acting. Weight and normal force cannot act in the plane that you are looking at. Okay, you are looking at the ground and the road on the ground. Okay, friction is the only force which can act in that plane. Right? So it means friction should provide centripetal as well as tangential force. Okay, think on those lines, all of you. The speed is given, the rate at which it is speeding up is given. You know the speed with which it is turning, you know the radius in which it is turning. So think of how to find out the amount of friction. Okay, listen all of you. Which force can provide the centripetal force here in this case? Which force can provide the centripetal force required? Centripetal force has to act in the same plane in which the car is moving, no? It should act towards the center of the circle. The only force which can act parallel to the ground here is friction. So centripetal force must be provided by friction. Tangential force also must come from friction itself. So basically these two should be the components of friction acting on the car. That means friction should actually be acting at an angle like this. What happened? Should be acting at an angle like this. Okay, static friction. It will have one component towards the center, that is in the radial direction, and it will have one component in the tangential direction. So it can help the car in speeding up. It can help the car in taking a turn also. Is this clear to all of you? Any questions in this? Or do you think there is some other force which can help the car speed up, or some other force which can help the car take a turn? No. Friction only has to provide both. Okay, because the person is pressing on the accelerator, the way the wheel rotates and it tends to skid in such a way that, I mean, it actually, like in this case, the tendency to skid will be in this direction. Okay, tendency to skid is this way because of the person pressing on the accelerator and also turning the steering wheel. The tendency to skid is in this direction. So the friction will act in the opposite direction as indicated in this diagram. So friction has to provide both tangential as well as radial forces. Okay. Tell me the formula for centripetal force. Make it fast, all of you. Anyone? Tell me the formula for centripetal force.
mv square by r.
mv square by r. Okay. Can any of you tell the formula for tangential force? Okay, I think this is the first time.
MA, sir.
M?
MAT. MA.
Okay. Vanilla, what did you say?
MA only, sir.
Okay, fine. Mass multiplied with tangential acceleration. Okay. And tangential acceleration is the rate at which speed is increasing or decreasing. Okay, this also we had discussed. So this becomes m into dv by dt, where v is speed. Okay. Now all required values are given in the question. Mass is not given. Mass is not required also. It will get cancelled. Okay. V square by r. V speed is given. Radius of the turn is given. Rate at which speed is increasing is given. Speed is increasing at a rate of 1 meter per second square. So dv by dt is 1. That is given. Now see, centripetal is in direction towards the center. Okay, it's in the radial direction. Tangential is in the tangential direction. What is the angle between centripetal and tangential force? Anyone? What is the angle between centripetal and tangential forces?
90 degrees.
90 degrees.
90 degrees. Radius, tangent, they are perpendicular. Angle is 90. These two are friction's components. Okay. Then how can you write friction? You can express friction this way. It's like the friction as a force. If you look at it, it is tangential force I cap plus radial force j cap. They're in the perpendicular directions. No, one component is in I cap direction, the other component can be taken in j cap direction. Therefore, magnitude of friction becomes root of Ft tangential force square plus centripetal force square. This is the amount of friction that is required to successfully take the turn while accelerating. If only taking turn is needed, all friction will act only towards the center. Then friction is equal to mv square by r. Directly you'll get the answer. If only speeding up is needed, friction is equal to mass into tangential acceleration. You'll get the answer. But here, car is speeding up and also taking a turn, and both can be done with the help of friction only. Now you can't expect two separate frictions to be acting, no? Okay, friction is one force between, it's a contact force between two surfaces. It can act only in one direction. Friction acts this way. One of its components helps in speeding up. The other component helps in taking the turn. Okay, so we found out how much force is needed to take the turn, mv square by r. We found out how much force is needed to speed up, m into tangential acceleration. Those two become the components of friction. By doing vector addition of those components, we are finding out how much friction is needed. And this needed friction, required amount of friction, should be less than or equal to the limiting value. From there, you will get the coefficient of static friction. Okay, so this requires some calculation to be done here. All values are given to you. You know dv by dt, you know mv. So it's like these two components are known. Normal force is mg. That is where m gets cancelled. You will have m on the left hand side of the equation and also right hand side, but it will get cancelled. G value you know, and from all that you can find out the coefficient of static friction. Okay, so I'll send you all the notes after class. You complete this problem. Okay. So what we discussed so far is how a vehicle can take a turn on a horizontal road. While taking a turn on a horizontal road, the forces acting on the vehicle are normal force upward, weight downward, and the only horizontal force that can act parallel to the road is friction. So friction must be helping it in taking the turn. So if the car or a vehicle is taking a turn without change in speed, no speeding up or slowing down, only changing direction, then all friction will be acting radially. We found out how much is the safe speed to take a turn. So remember, this is when speed is constant, not when the vehicle is accelerating or retarding. Okay, we solved some problems based on it. Then we discussed what to do if the vehicle is accelerating also, speeding up or slowing down. If it is speeding up, tangential force is in the same direction as motion. If the vehicle is slowing down, tangential force will be opposite to motion of the vehicle. That's all. But that also has to arise from friction only. Okay. So this speeding up, slowing down case is actually advanced level. For mains and all neat mains, they'll ask about taking a turn with constant speed. Okay. Right. So if road is horizontal and speed is constant, then V should be less than or equal to under root mu s into r into g. So this is the maximum safe speed for turning without skidding. Okay. Now, have any of you observed hilly roads on a hill? Is there any difference between a normal road, normal city road, and roads that you find on hills while climbing hills?
Yeah, sir. They're more uphill over the mountains.
They are more,
Uphill, up.
of course, that slope will be there. Any other difference you noticed? Or you think of this, let's forget hilly roads. Let's take normal roads only, but a race course. Okay, you imagine a race course. The roads that you find on a race course and the normal roads that you find in cities, what is the difference between them? Don't
More
say
turns are there, sir.
more turns are there. Okay. In city roads also there are more turns only. But how is the construction or what do I say? How is the road different? Of turns, okay, number of turns you put that aside. What else? Any other differences you noticed?
Smoothness of road.
I know one of you, I was expecting that answer also. City roads will have potholes. Race roads won't have potholes. Smoothness of road. Correct, correct, correct. What else?
Sir, the hill road will be slightly uphill when going up, like it's slanted a little bit.
Like, are you saying about upslope and downslope, or are you saying tilt in the road? Talking about tilt in the road.
Tilt, sir, tilt in the road.
Okay, you are talking about a tilt in the road. Have any of you noticed that on race course roads? Like, I don't know how many of you actually watch races and all. Okay, just a moment. Let me download one image. You'll understand better. One second. Okay, observe this, all of you. This is an Olympic cycling track, indoor cycling track. You observe that track, okay, the actual path on which the cycles are moving. That is, does it seem to be a horizontal road? Like the turf that you see, the surface that you see here, this is horizontal, this is level. Okay, but the actual track on which the cycles are moving, is it horizontal or is it tilted? What does it look like?
Tilted, sir.
It is tilted. Okay, why do you think the track is tilted? Like on hilly roads also, I'm sure you all must have observed this. On hilly roads, when there are turns, okay, the road will be tilted like this. It won't be horizontal, it will be built at an angle. Okay, why do you think the roads or the tracks are designed like that near turns? Any idea? Okay, even on race tracks, okay, like car race, bike race tracks, that tilt can be observed. Why do you think the roads are made like that? Okay, consider this image. This is too much of a tilt actually, but still, sometimes it may be needed. Just a moment. Okay, so basically we are talking about the difference between these two situations. On the left, you have a horizontal road. On the right, you have a tilted road. Tilted road is also called a banked road. Banked road. Okay. Now see, when a vehicle moves on a horizontal road, observe the forces acting on it. As usual, weight will act vertically downward. Okay. And because the road is horizontal, normal force will act, it will have to act vertically upward. There is no other way. Normal force acts this way, weight acts in the downward direction. And friction will act parallel to the ground. Maybe this way, maybe this way. Okay, maybe forward, maybe backward, depending on whether the vehicle is speeding up, slowing down, taking a left turn, taking a right turn, depends on that. So on a horizontal road, this is how the forces act on the vehicle. Now you consider a banked road. You can see that the road is tilted and accordingly the vehicle is also tilted. Now, as usual, mg will have to act this way only, it has no other choice. Earth's gravitational pull will be in this direction. But can any of you tell me in which direction the normal force will act this time? In which direction will the normal force act? Yeah, generally, normal force acts in which direction? Why are you all silent?
Upward, sir.
Why will normal force always act upward? Upward means you have to be specific.
Like opposite to the mg.
No, why should normal force act opposite to mg? Does it
So
have any
perpendicular to contact surface.
perpendicular to
Contact surface.
surface of contact? Correct. See, the reason it's called a normal force, normal itself means perpendicular. Okay, so normal force now acts this way. Okay, normal has no relation with mg. Okay, Normal acts perpendicular to the surface of contact. So on all 4 wheels or 8 wheels or whenever wheels the bus has, together the normal force will be acting like this. Okay. Now, if it's a smooth road, if there's no friction, the vehicle may skid down the road like this. It may skid up the road also. If the vehicle moves too fast, it can skid upwards also and fly off. Okay, skid outwards. If it moves too slow, it may skid downwards like this. So skidding is possible. And to prevent skidding, it could skid down the road like this. It could skid up the road like this. There is one case in which it can move without skidding also. But to prevent skidding, friction may have to act down the road. It may have to act up the road, or in some cases, it may need not act also. If the vehicle moves at a correct speed, there is no need for friction. The vehicle will automatically take a turn. Now, to take a turn, we need a centripetal force. If there's no friction, who will give centripetal force? We'll discuss all that. Okay. So imagine a curved road like this, banked road is what we call it. Okay. Assume there is a vehicle. Okay, it's difficult to draw. Just a moment. Anyway, let's not waste time on this. Let's say there is a vehicle like this. Wheels will be there. Actually difficult to show the curvature. Fine, let's take the front view. So if you look at it from the front, this is a tilted road. Okay, let's say the road is tilted at an angle theta. This angle theta is called the angle of banking. And when you look from the front, it will appear like this. This is one wheel, another wheel. The vehicle will be tilted this way. The forces acting on it, as we have discussed, mg in this direction, normal force in this direction. Okay, we'll talk about friction. For now, let's assume it's a smooth road, no friction. Now, this vehicle, which is say somewhere here, with weight acting this way, normal force acting this way, has to take a turn like this. So we need a centripetal force in this direction. Okay, we need a force acting on the road towards the center of the circle. Okay, so if you imagine the road here, the center of curvature of the road will be somewhere here. The vehicle will be turning in a particular radius. Now, if you observe, the normal force is acting at an angle. You can consider its components. One component of normal force acts towards the center of the circle. The other component of normal force has to balance mg. Okay, so if the angle of banking is theta, then this angle also will be theta. See, had the road been horizontal, normal force would have been vertical like this. If you tilt the road at an angle theta, the normal force vector also rotates by the same angle theta from the vertical. So what will this be? N cos theta. And what will this component be? N sin theta. So this is why roads are banked at near turns. If you bank the road, okay, if you build the road like this, normal force also will be helping in taking the turn. So the vehicle won't be relying completely on friction only. There's a normal force which helps you take a turn. There's a component of normal force which helps you take a turn. So it will be much easier to take the turn, much safer to take the turn. Okay, that is the purpose of banking a road, building roads tilted. And why it is done on racetracks? Because on racetracks, vehicles are expected to move very fast, but they have to take a turn also. At such high speeds, taking a turn on horizontal road makes the vehicle rely only on friction. But with friction, the maximum speed at which you can take a turn is only this much on a horizontal road. But if it's a banked road, normal force also supplies some centripetal force. Okay, so you can increase the speed. You can take that turn at higher speeds. Fine. That is how banking a road makes it safer for taking a turn. Is this clear to all of you? Any doubts in this? Okay. So if you consider a vehicle taking a turn on a smooth banked road, fine, the vehicle moves in a horizontal path itself. Like if you consider, okay, just a moment. Okay, just to show you the track, complete track, you can consider this image. So you can imagine it like a plate. Okay, those ceramic plates will be there now with raised edges. So that raised edge is the banked road for us. Okay, so the plate's edge, it is horizontal only. It is tilted, but it is horizontal, parallel to the table, parallel to the ground. Okay, so the vehicle moves in a horizontal plane. It doesn't move vertically upward or downward. It takes a horizontal turn. Right? Just a moment. Okay, I am not able to find a proper image of a ceramic plate. Never mind. So the vehicle takes a horizontal turn. So vertically, the forces should be balanced. So suppose the vehicle is somewhere here. mg should be balanced by n cos theta. And n sin theta should provide the centripetal force. So we can write n cos theta is equal to mg. N sin theta, if there's no friction, n sin theta is the only force which can provide the centripetal force, is equal to mv square by r. First equation. Second equation. You do second equation divided by the first. Left hand side, n sin theta divided by n cos theta. Sin by cos becomes tan theta. Is equal to right hand side, mv square by r divided by mg. M gets cancelled. You will be left with v square by r divided by g. That is v square by rg. So you get v square is equal to rg tan theta, where theta is the angle of banking. So v is equal to under root rg tan theta. So what have we derived here? We have derived the speed with which a vehicle can move safely on that banked road without skidding. Okay, so this is called optimum speed. In fact, if the vehicle maintains exactly this much speed, there is no need for friction. We derived this speed without considering friction to be acting on the vehicle, right? N sin theta is sufficient to help it take the turn. So n sin theta will be enough to help it take the turn if it moves with exactly this much speed. Under root rg tan theta, that speed is called the optimum speed. So even if the road is rough, if vehicle moves with this speed, friction won't act. We know friction is a force which comes into play only if it is necessary, right? If the vehicle moves at this speed, n sin theta is enough to make it take the turn. So the vehicle is not going to skid anyway. Okay, it won't skid out of the road. It won't skid into the road also if it maintains this speed. So if the vehicle moves with this speed, even if the road is rough, no friction will act on it. It can safely take the turn. Okay. What if the vehicle moves faster than, see, practically it is impossible to maintain an exact particular speed. Okay, the vehicle will either go faster than this or slower than this. So if the speed of the vehicle is greater than the optimum speed, you consider this bus itself moving on the banked road. If it maintains that exact optimum speed, then without the need for friction also, it will be able to take the turn. Like you can see, it's between those white and yellow lines, right? It will stay between those white and yellow lines. It won't come down the road. It won't go up the road also, if it maintains that optimum speed. Okay, so it will be able to safely take that turn. Now you all like use your own logic and tell me, if the vehicle moves faster than the optimum speed, will it have a tendency to skid outward like this or to skid inward like this? Or will it maintain that position even with higher speeds? If the vehicle moves with a speed more than optimum speed, will it have a tendency to skid up the road or skid down the road? Or will it still not have any tendency to skid?
Sir,
Sir,
it
I
may
think it
skid
go
down
down the
the road.
road.
Okay, Rishi is saying it may skid down the road. Okay, Vanilla, what were you saying?
Sir, it may skid down the road.
Down the road. Okay, why do you think so? Like, if the vehicle is moving too fast, why will it go inwards? Okay, let us look at that horizontal road diagram once. This case. Okay, you all tell me. Now see, on a horizontal road, there is one, I mean, there is a limit to the speed that the vehicle should maintain. If the vehicle goes too fast, okay, it's trying to take the turn, but it is going too fast. Will it have a tendency to go out of the road like this, or will it have a tendency to go into the road like this? One or two. What is going to happen if the vehicle moves too fast? If you try to take a turn with too much speed, will you skid out of the road? I mean, out of the turn, or will you skid into the turn?
Sir, into it only, sir.
This is surprising, actually. Okay, others, what do you think?
Sir, out of the road.
Out of
Out.
the road, sir.
See, it will skid out of the road. See, naturally, because of its velocity that is there in this direction, it tends to move in this direction. Okay. If friction is sufficient, it can stay on the road. It can take the turn safely. If speed is too much, friction won't be sufficient to help it take the turn. If if there is not sufficient help to take the turn, then it will go out only. No, how will it turn sharper if help is not sufficient? If speed is too much, how will it take a sharper turn? That I'm not able to understand. Rishi, what do you say now?
Yeah, sir, understood. My bad.
Generally, some others also thought it'll skid inwards. The vehicle skids outwards if it moves too fast, because if it is going too fast, centripetal force mv square by r, if speed is too much, we need more centripetal force. Where will it come from? Friction is limited. You can't get how much ever centripetal force you want. Okay, so you will not be able to take the turn safely. If you are not able to take the turn safely, it means you will go out of the road like this. Okay, so if a vehicle moves too fast, skidding will be outwards, not inwards. Okay, so same thing here. If this bus travels too fast, or let's assume it's a road without friction, smooth road, oily road, whatever it is, oily track. Okay, if it maintains the speed under root rg tan theta, optimum speed, then it will take the turn safely. Taking turn safely means what? I'll draw here. It will move along this path. Okay, let me change the color a little bit. Okay, if it maintains optimum speed, it will be able to stay at that level. If the speed is more than optimum speed, then what will happen? The bus will go up the road like this. It won't be able to take the turn. It will have a tendency to go out. This is what happens if the speed is more than optimum speed. The green path is what it will take if the speed is equal to optimum speed. Suppose it is too slow, or you imagine the bus to be at rest. Okay, suppose it's not moving, it is at rest, but the road is oily, then the bus will skid down the road, no? So if the speed is less than optimum speed, then what happens? The bus will skid inward like this. Okay, so if the road is oily, no friction, exact optimum speed, if it maintains, it will stay on track. If its speed is more than optimum speed, okay, then it will go out of the track. If its speed is less than optimum speed, it will slide down into the track. Okay, now see, if the speed is more than optimum speed, it has a tendency to skid outward. In that case, friction will act inward like this. If it has a tendency to skid outward, friction will act inward. Suppose the speed is less than optimum speed, it has a tendency to skid down the road, then friction will act up the road like this. Friction has to prevent sliding, prevent skidding. So depending on the way the vehicle is going to skid, friction will act. So is this clear to all of you? Is this picture clear? Any doubt in this?
Yes, sir. It's
Others also, if you have any questions, you can ask. Okay. So if the speed is more than optimum speed, tendency to skid is outward, friction will act inward. Okay. It's like vehicle tends to skid up the road, friction acts down the road. Let us discuss that case today. Suppose the speed is more than optimum speed. Where is that banked? Okay. Right. So speed is more than the optimum speed. It has a tendency to skid up the road. Friction will be acting down the road. Now friction also has two components here. One component this way towards the center of curvature of the path and another component downward. How much will these components be? If that angle is theta with the horizontal, then this angle is also theta. This becomes F cos theta and this downward force becomes F sin theta, and that acts along with mg. Okay. Friction has to act parallel to the road. Here the tendency to skid is up the road. So friction acts this way, down the road. It'll have one component towards the center of curvature and one component along with mg in the direction of mg. So that is what we have indicated here. Normal force acts perpendicular to the surface of contact. It will also have two components. And as usual, when we visualize the components of the force, you don't actually have to consider the original force. Same with friction. We have considered the components of friction. Okay. Now the vehicle takes a horizontal turn. Means vertically it should be balanced. In the vertical direction, there is equilibrium. So tell me all of you, what force is acting in the upward direction on this vehicle?
N cos theta, sir.
N cos theta is acting upward, correct. Upward means perpendicular to the ground level, not perpendicular to the road. So N cos theta is acting upward. What force or forces are acting downward?
F sin theta and mg.
Mg and F sin theta, correct. Where F is the friction acting on the vehicle. So this is balancing these two. Vertically, the vehicle doesn't move. It moves horizontally, like the edge of the plate, as I said. It has to move along the edge of the plate. It doesn't have to go perpendicular to the table upward or downward. It has to stay on the edge. Okay. So this is one equation. Vertical equilibrium gives us this equation. Horizontally, the vehicle is not in equilibrium. It's taking a turn. Taking a turn means accelerating, means there must be a net force acting on it. Horizontally, we write centripetal force is equal to mv square by r. Okay. What forces are acting towards the center of curvature of this path? Center of curvature of this path is this, C. What forces are acting on the vehicle towards that direction?
N sin theta and F cos theta.
N sin theta, F cos theta are both acting. Okay. So you can say N sin theta plus F cos theta together provide the centripetal force, mv square by r. These are the equations. Okay. So what is our aim here now? We need to find out, like suppose the coefficient of friction is known to us. We need to find out the maximum speed with which a vehicle can take a turn in the presence of friction. Without friction, there's only one speed, optimum speed. If it goes at that speed, it'll stay on track, it won't skid. If it goes faster, it'll skid outwards. If it goes slower, it'll skid inwards. So without friction, there's only one safe speed. But with friction, the vehicle can afford to go a little faster. Why? Even if it goes a little faster, it tends to skid upward, but friction will prevent that skidding. So it can go a little faster than this optimum speed. So we need to derive what is the maximum safe speed. Suppose vehicle is moving at maximum safe speed. Okay. That means extreme case. If it moves even a little faster, it will skid. So friction is trying its best to prevent skidding. So if it is moving at the maximum safe speed, that means limiting friction must be acting. All available friction must be acting. Right? If it goes at optimum speed, friction is not even needed. It will anyway stay on track. If it goes slightly faster than optimum speed, it has a tendency to skid outward. Little bit of friction will be needed to prevent skidding. If it goes much faster than optimum speed, much greater amount of friction will be needed. So if it is going at the highest possible safe speed, all available friction will be acting. So in place of F in these equations, we have to take limiting friction. Okay, let's consider these two equations as it is. First equation we have is N cos theta, vertical equilibrium, N cos theta is equal to mg plus F sin theta. This time it will be F limiting sin theta if the vehicle is going at its fastest possible speed. And the other equation becomes N sin theta plus F cos theta is equal to m v max square divided by r. When the speed is maximum, friction is maximum. That's the idea here. Okay. Our aim is to derive that maximum speed. Fine. Limiting friction, we have a formula for it. Mu s n. We can substitute the same here also, mu s n. Now the first equation can be rewritten as n cos theta minus, send the normal force term to the other side, mu s n sin theta is equal to mg. And the second equation can be written as n sin theta plus mu s n cos theta is equal to m V max square divided by R. Now you do second equation divided by first. Okay, lengthy derivation only, but it's a proper application of what all we have learned in this chapter. Second equation, n sin theta plus mu s n cos theta divided by first equation, n cos theta minus mu s n sin theta. Right hand side, second equation, we have mv square by r. That is maximum speed. Right hand side, first equation, we have mg. Okay. On the left hand side, normal force can be taken common in the numerator, denominator, it will get cancelled. Right hand side, mass gets cancelled. You will be left with V max square by Rg is equal to sin theta plus mu cos theta divided by cos theta minus mu sin theta. Therefore, send Rg that side, take square root. The maximum safe speed with which the vehicle can take a turn on a banked road is under root Rg into all this. Sin theta plus mu cos theta divided by cos theta minus mu sin theta. You don't have to remember this expression, but remember how it is derived. Okay, that free body diagram is the most important one. This is diagram indicating the forces. Speed is more than optimum speed, so tendency to skid is this way. That's why friction will act this way. And then you resolve them into components and write equations, Newton's second law equations. Vertically, it's in equilibrium, balance the forces. Horizontally, the force equated to centripetal force. Okay, suppose theta is 0. Tell me what this equation will become, any of you? If theta is 0, means the road is not banked. How much is the maximum speed?
Rg into mu, sir.
If theta is 0, sin theta becomes 0, cos theta becomes 1. This is 1, this term is 0. So the result changes to under root Rg. Numerator you will have 0 plus mu, that is mu. Denominator you will have 1 plus 0, that is 1. So it becomes under root mu Rg, and we have already derived this. Okay, that's the first derivation that we did today. If the road is not banked, the maximum safe speed is mu Rg. So the banked road formula also tells you the same thing. If theta is 0, the maximum safe speed is mu Rg. Okay. So on a banked road with friction, this is the maximum safe speed with which the turn can be taken. If the vehicle goes faster than this, then it will skid out of the banked road also. Normal force, friction, both won't be sufficient to prevent skidding. Both won't be sufficient to keep it on track. Okay. Now, as homework, I want you all to derive the minimum safe speed that the vehicle can maintain. Now, we had discussed that also. If speed is less than optimum speed, the vehicle will have a tendency to skid down the road. Then in that case, friction will have to act upwards. So the free body diagram will change a little bit. The forces you will have to adjust the equations. I'll give you some hints in the worksheet. Tomorrow's worksheet, you'll have to do this. So you have to derive the minimum safe speed on a banked road. Maximum safe speed is this. Okay. So what all have we discussed today? Basically, we are continuing the discussion on forces involved in circular motion. Today, the topic was how a vehicle can take a turn on a road. With friction, without friction, all those cases. On a horizontal road, without friction, taking a turn is not possible because normal won't have a component towards the center. Normal will be acting perfectly vertical. No force towards the center. So taking a turn without friction is not possible on a horizontal road. So with friction, we discussed what happens, how much maximum speed, how much coefficient of friction is needed. What if the vehicle is accelerated, means speeding up? We went a little ahead also. Then if you need to take turns at high speed, the turn has to be banked. The road itself has to be banked. Okay, that can help you take a turn at a greater amount of speed. That was the next thing that we discussed. A banked road, how does it help in taking a turn at greater amount of speed? On a banked road, the normal force will have a component which adds to the centripetal force. Okay, so we are not entirely relying on friction. Normal force also helps us take the turn. So we can go at a greater speed on a banked road. Okay, so we found out what is the maximum speed with which a turn can be taken on a banked road. You derive what is the minimum speed with which we can take a turn. Little bit more is left in this chapter, conical pendulum, and some problems we'll solve in the next class. After that, laws of motion will be complete. I think this is the lengthiest chapter of 11th class. Yeah, even system of particles, one more chapter is there, slightly longer than this. But see, these ideas are very important. As I said, the concept that you learn in laws of motion, next chapter, work, energy, power, and the chapter after that, system of particles. These concepts will be applied in all chapters after this. Okay, 11th and even in 12th class, you'll use these ideas. Okay, so we'll spend more time on this, and you also have to do more work from your side. Solve more and more problems from this chapter. In your school, you may have passed this chapter already, or you may you may be yet to cover this chapter, whatever, but you have listened to some concepts in my classes. So start solving problems based on laws of motion. Any reference book that you have or your material from your institute, take that and keep solving problems. Okay. So we'll stop it here for today. If you have any doubts, you can ask.